Satyam Prabha. Digital India. Educated India.
Good morning, students. So today we will start a new chapter where we will deal with a special mathematical model which comes handy in solving various problems. And it's not only in computer science, but also in many other domains. This abstraction is used for solving various real world, for modeling and then solving various real world problems. So what I'm talking about is graphs. So I guess some of you have already come across the name of this particular mathematical model, but we will in this course of lectures we will get to know more details about them. So graphs they can be thought of as a mathematical concept. And this mathematical concept is typically used to model some real world phenomena, okay, that can be abstracted as a collection of entities and relationships among these entities. So these two words are very important: entities and relationships. Okay, this is what a graph is typically used for. So mathematically, let us try to define what a graph is. Okay, so mathematically, a graph G, written as VE, okay, is a pair of sets. Okay, where V is called the set of vertices, and this is mandatorily non-empty. The set of vertices in a graph cannot be empty. Okay. And E is the set of edges. Okay. Now, V actually is encoding some property of an entity. Okay. You remember I just now talked about entity. Okay. So V is some sort of an encoding of some property of an entity. Sometimes V itself is also, called as entities. Okay. So it's basically a vertices are nothing but a set of entities. You can think of it like that. Okay. And E is the relationships between the vertices. Okay. Read entities. Okay. So what I want to mean here is that uh, V actually denotes an entity, and this entity could be denoted by some specific property of the entity. Could be as simple as a label indicating that entity. Okay. Or you can think of like a social network like Twitter. Okay. Here V is the set of users and E is the set of followers and followings. Okay. So this is how the vertices and edges of a Twitter social graph can be thought of. Okay. So and here each V or each node is a user, which is an entity, and the entity has different properties like a name, a geographic location, an edge, and many other different uh, indicators or properties which are typically called or which typically make up the profile or the user profile of that user. Okay. So this is just an example to motivate you. So mathematically, what is E? Okay. So again, here we will try to connect the second dot with our discrete structure course. Like we have already seen in complexity analysis, some connections between the two courses. Here again, while defining E, we will see that we have to invoke some of the set theoretic ideas that you have already come across in the discrete structures course. Okay. So E, as I said, is denoting a relationship. Okay. This is usually represented as a pair of vertices. Okay. This you read as there is a as if a relationship between the vertices. Sometimes vertices are also called nodes. Okay, between the vertices U and V. Okay. So therefore, E is in specific a subset of V cross V. Okay. So immediately, I think this takes you back to relations. Okay. To the idea of relations. So basically, E is a set of ordered pairs okay, chosen from V cross V. So this is how you interpret E set theoretically. Now, if two vertices or nodes are connected by an edge, then the vertices are said to be adjacent, okay, or neighbors of each other. So, in other words, if UV is an edge, then U is a neighbor of V and vice versa. Sometimes, if in a graph a node is not adjacent to any other node, then such a node is called an isolated node or vertex. Okay. So these are some of the definitional terms that you need to remember when we proceed with our graph algorithms later on. So a graph further is finite if it has a finite number of nodes and edges. Else the graph is infinite. So a finite graph will have a finite number of nodes and edges. Okay. Else such a graph which has infinite number of nodes or edges is called a infinite graph. If G is finite, then modulo V represents the number of nodes in G. Similarly, modulo E represents the number of edges in G. So this term, the number of nodes in G is, or modulo V, is sometimes called the order of the graph. Similarly, the number of edges is sometimes called the size graph. So given these basic intuitions, pictorially, a graph G would look like as the following. So here V, or the set of vertices, is A, B, C, and D. The set of edges is AB, AC, BC. The order of this graph is 4, since it has 4 vertices, and the size of this graph is 3, since it has 3 edges. Now, there can be different ways of categorizing a graph. Okay, the first categorization that we will look into are the undirected and directed graphs. So a graph G is directed, sometimes also called a digraph, when the direction from one vertex to the other is defined. Okay. Otherwise, the graph is called undirected. So in terms of notations, normally a directed edge from U to V is usually represented using arrow brackets. Okay. An undirected edge from U to V is usually represented using parentheses. So once you have these notations, you can write that UV is not same as VU because there is a directionality involved. Okay, whereas UV is equal to VU. So in the previous picture that we saw, the graph was undirected and therefore UV there was same as VU. A directed graph could be as follows. Now note here, there is a directionality involved and this is usually denoted by the arrow on the edges. Okay, so there is an edge from A to B, but there is no edge from B to A back. Okay, similarly there is one edge from B to C, no edge from C to B back. Okay, now you can also have a graph which is like this. Where edges run in both directions. So there is an edge from A to B as well as there is an edge from B to A. Okay, so that's why we said in the previous slide that in directed graphs, remember UV is not same as VU. The next thing that we need to introduce ourselves to, again a very important concept, is a weighted graph. Now, sometimes there might be weights present on the edges of a graph G, could be both directed or undirected. Okay, so an example of such a graph is like this. So there could be edges with numbers on them, okay, or weights on them. So these are called weighted graphs. Now, why are such graphs useful? So these kind of graphs, okay, could actually indicate the cost, okay, related to an edge. Okay, so suppose your real world problem is modeling, distances across or modeling roads across cities. Okay, and these edges could represent the distance from city A to city B. Okay, and so this number here on the edge is kind of showing that the distance between city A and city B is 2 units. Distance between city B and city C is 5 units. Distance between city A and city C is 6 units. So there could be various such interpretations of the weights on an edge. Okay, or it could represent like the cost of going from city A to city B. Okay, cost of going from city B to city C. It could represent distance, it could represent cost, it could represent various different things, or it could even represent, you know, how similar the two nodes are. Say for instance, like on some scale, B and C are similar to the extent of 5, A and C are similar to the extent of 6, A and B are similar to the extent of 2. So there could be various different interpretations: cost, distance, similarity, etc. As we go on with more information about graph algorithms, this idea of weights will become more and more clear. So the next thing is self-loop. So an edge that starts from a node and comes back to it is called a self loop. Okay. So an example once again. So here, this particular edge is a self loop. So in terms of notations, we will describe this edge as BB. So that is the start and the end point of the edge is the same vertex B. Now a similar concept is that of parallel edges. So these are pairs of nodes connected by multiple edges. Okay. So if in an undirected graph we have two edges, say Vi, Vj and Vp, Vq, such that Vi is equal to Vp and Vj is equal to Vq, then these two edges are parallel edges. So an example is like this. So this portion here in the picture represents a parallel edge. Now the next thing is a very important concept, and this is something that you will need time and again in this will appear time and again in various graph algorithms. So this is about a path in a graph. So a path in a graph is a sequence of vertices such that from each of its vertices there is an edge to the next vertex in the sequence. So clearly both vertices and edges can be repeated in a path. So in other words, a path from, say, the vertex U to the vertex W, okay, can be represented as a sequence of edges like U V1, V1, V2, and so on and so forth, and Vk minus 1, W, as if connecting U and W through a set of edges. Or indirectly, connecting U and W indirectly. The number of edges counted in a path is called the path length. Okay, so for instance, take the example I showed you just now. So here an example of a path could be so AB BB, BD, DC, CB, BD, DE. So you can trace the path. So AB, BB, BD, DC, CB, BD, and DE. So this is a example. This is an example of a path in this graph. Okay, and this path has length, number of edges 1, 2, 3, 4, 5, 6, 7. So this path has a length 7. Okay, a path with no vertex repeated is called a simple path. So this also means that there is no duplicate edge. So in this particular example again, AB, BD, DE is a simple path. Okay, AB, BD, DE is a simple path. Fine, because none of the vertices are repeated here, and similarly none of the edges are repeated. Similarly, a path with no edge repeated is called a trail. However, in a trail, vertices might repeat. Okay, in a trail, edges do not repeat, but vertices might repeat. So a closed trail is a one where the start and the end vertices are the same. So in general, a closed path is a path where the start and end vertices are same. Otherwise, it's an open path. So if the start and the end vertices are not same, then it is an open path. So edge repetition is allowed in an open path, okay, or also in a closed path. However, if this path is a trail, then edge repetition is not allowed. Again, continue with the same example. AB, BD, DC, CB, BD, DA is a closed path, okay, and here as you see BD is repeated. A cycle is a closed path. Sometimes a cycle is also called a circuit or a tour. Okay, is a closed path of non-zero length. Okay, remember these keywords. A cycle, again, this is an important definition. A cycle is a closed path of non-zero length that does not contain any repeated edges. Okay, a cycle is a closed path of non-zero length that does not contain any repeated edges. Okay. However, vertices may be repeated. For instance, in this particular example, is a cycle. So here all edges are distinct, but the vertex B is repeated. And you see here in this from this example, it is apparent that a bigger cycle may contain a smaller cycle. For instance, in this example, this cycle AB, BB, BD, DA has a smaller cycle BB. A simple cycle, on the other hand, is a cycle that does not have any vertex repeated except the start and the end vertices. For instance, in the previous example that we saw, AB, DD, DA is a simple cycle. The next in line is a connected graph. So a graph is called connected if and only if any pair of nodes UV if for any pair of nodes UV there exists at least one path from, or rather in a more generalized sense, one path between U and P. Okay. If the above is not true, then the graph is called disconnected. So that is, between every pair of nodes, you should be able to find one path at least. Okay, then such a graph is called a connected graph. So any pair of nodes you take up, you should be able to find at least one path, okay, between the pair of nodes. If that is not true, then the graph is disconnected. For instance, this is a connected graph because you find a path from every node to every other node. In fact, this itself is also a connected graph. Okay, you might immediately see that every pair of nodes you take up, you should be able to reach another node in the graph through a set of edges. For instance, if you pick up C and want to go to D, you have CA and AD. Okay. Similarly, if you pick up B, you can go to BA and then B to A to D. Okay. However, if the example was like this, then this would be a disconnected graph because there is no way to go to. So for directed graphs, there can be two types of connectivity. The first of these is called a strongly connected graph. So a graph is strongly connected if and only if every pair of vertices in the graph is reachable from one another. That is, there are directed paths in both directions for every pair of vertices. The other type is a weakly connected graph. So the trick is simple. Replace all the directions. If the resultant undirected graph is still connected, then the graph is called weakly connected. So basically replace all the directions with no directions. So if the resultant undirected graph is still connected, that is, there is an edge between every pair of nodes, then the graph is called weakly connected. Sorry, there is a path between every pair of nodes. However, in the undirected graph, if there is a path existing between every pair of nodes, then we call it a weakly connected graph. So strongly connected graph means that there will be a directed path in both directions. Okay. For example, this particular graph is a strongly connected graph because there is a directed path between every pair of nodes. While this one is a weakly connected graph because its undirected version is a graph that is connected. Okay, because there is a path between every pair of nodes. Next is a simple graph. So a simple graph is a graph which neither has a self loop nor parallel edges. Okay. So a simple graph neither has a self loop nor parallel edges. However, simple graphs can have cycles. Simple graphs also can have isolated vertices. Both these are possible. The next thing is the degree of a node or vertex. So in an undirected graph, the degree of a node is the number of edges incident on the node. So let's say this is a node A. So in this example, the degree of node A is equivalent to the number of edges, that is 1, 2, 3, and 4. Okay, so degree of A is 4. Okay, so sometimes this is represented as degree of node A in graph, say G, is 4. In directed graphs, again, there are two types of degrees, the in degree and the out degree. So in degree is the number of nodes, number of edges. So in degree of a node is the number of edges moving into a node. Out degree is the out degree of a node is the number of edges moving out of a node. Okay. Sometimes we will denote this as minus and B plus. Okay. So for instance, if we again take this example, here degree, and let's say this is the graph G, degree of C minus, that is the in degree, is 2, and degree of C plus, that is the out degree, is 0. Because there are two edges moving into C and there are no edges moving out of C. Similarly, degree plus of B is 2 and degree minus of B is 0. Because there are two edges moving out of B and no edge moving into D. So we'll stop here. Next class, we will look into different spatial types of graphs.